Hi everyone, we'll just wait a few more minutes to let the last few people join before we start the talk today. Thank you. Okay, I think we'll start. So hello everyone, welcome to the second seminar of this Landscapes Live Spring 2024 series. It's great to have you all here. It's my pleasure today to introduce Albert Cabré, who's going to talk in just a moment about his work looking at landscape change in the Atacama Desert as a result of rainstorm events. Before he begins, I just want to flag next week's talk, which will be by Scott Jess from Washington State University, looking at the ups and downs of extensional tectonics. But now I can hand it over to Albert. Thank you very much for putting together this talk. As ever, everyone, if you could refrain from posting in the chat until the very end. Any questions that you do have, please feel free to use that chat tool. Yeah. Okay, great. Handing over to you, Albert. Thank you.
Okay, thanks for having me. This is a nice opportunity because we've been working for some time now with some of the colleagues that I've spotted here, but also some others that also collaborate. We collaborate together. But the idea of what I wanted to present today is based on the last, let's say, the last 8-9 years recent rainstorm events, to show you some of these the consequences of these events, and this will happen in the Atacama Desert. And most of the research in this area has been supported by the Chilean research agency, which is ANID, and also by University of Chile and other universities. But from the French side, where I did my postdoc at the special agency, French special agency, I also want to thank the Programme National de Detección Espacial and the JET for the support along these years. Well, this talk will offer you a combination, let's say, of field examples, so examples of geomorphic change during events that we started to monitor from 2014 to the present. And the idea is that since I've been working on that, I will also talk about how we integrate remote sensing and in particular synthetic aperture radar products to understand where and when at regional scales these surface changes occur during these known rainfall events. The idea behind all of this connection, let's say, is to assist in identifying the path through which the sediment in this arid landscape moves during these extreme storm events. But first, I want just to make a brief introduction into what and where are drylands. So you can see that they are almost in every continent in our planet, and they cover a large area. It's up to 40%. And the area where we will be talking today is the Atacama Desert, which is in South America. It's a long strip, but it's quite large. And these landscapes erode or being they are the erosion processes that operate in these landscapes are mostly related to water erosion, which happens only during these intense short-lived rainfall events that produce enough surface runoff to entrain sediments, and other processes which I will not be speaking here today. It's about with erosion, or for example, in the Atacama, it's also quite interesting to consider seismic shaking related processes and other that will not be discussed today. So why study surface runoff in drylands? It's because this is as I shown you, is a widespread problem, which is particularly intense in drylands, and can be very fast, as you see in these two pictures from the Copiapó River on the 25th of March, almost 9 years ago. We see that during these heavy rainfall events, there's a lot of sediment being transported, but we still do not know how exactly this works, or let's say that it's still poorly studied, which might be a better wording for that. Well, this is not a surprise that in drylands there is such as the Atacama Desert. So this is, for example, the accumulation of almost 30 years of precipitation. It's close to zero. So okay, we do not capture any. There's not significant information on this map, apart that it's highlighting that this is a desert area, but we know that in drylands, usually when these rains happens, they are convective cells which are randomly distributed in space. I just put it here an example from Sharon 1972, working in the Najd Desert, but meaning that this is something which it's already understood that it works that way. And this intense and short duration, as I will try to show in this video, this is from the event from March 2022 in a small town in the Atacama Desert. You will see that this is quite lucky people being the houses being flooded. What I want to show you here is that also there's a lot of hail on the ground. So this is an indicator of how intense and this kind of rain cells can be in the desert. So once that's said, this makes us miss how sediments move during rainstorms, because what we have available, at least in the Atacama, as I show you here, this is from Teresa Jordan and collaborators' paper, but this wants to show you only the isojets for the March 2015 event. But you will see that the black spots, some of them are cities, but the others, the smallest ones, are rain gauges, so they are really scarce, and we will see that they are mostly situated on the valley floors. So we get to have no information in between valleys. So there is very scarce information about how rains fall or how rainfall is distributed in these areas, and also satellite compilations, let's say, like for example this one from the IMERC volume version 6, which encompasses the event of the March 2022. Sorry. For example, misses this was the video area. So this point here would be the video area. So the intensities that they're really happening on the landscape, we are not able to record it here because of course of this coarse resolution, but also probably because of some technical limitations which I'm not really expert on. But let's say we do not have the tools yet to understand this with what is available. So this talk, apart from navigating, will be divided into parts. The first part is when and where runoff erosion happens. and I will be using recent rainstorm events, mostly the March 2015 one in Atacama. And the other part of the talk, would be how grain size changes in valley floors such as this one, and to give some insights about how sediment is being transported during these events. So again, why to study runoff erosion, but in this case in the Atacama Desert, is because we have people living in there. So this needs to be addressed in order to address mitigation strategies which are more efficient than having floods, towns completely flooded and devastated during these events. And the Atacama, it is also interesting. We know that it's probably one of the oldest deserts in our planet, but we can go and study, let's say, recent, but not that recent. So it's more than 30 years old, but we can go and study debris flows, for example, that they look as they were deposited probably last week. So we know that the Atacama is divided into these 4 countries here in South America, but so that's what we know. So we know that it rained. It's a bit obvious, but okay, it rained. We have coaches, eyewitness reports, ourselves getting wet, and my other Chilean colleagues. And we know that there's flooding on the valleys, and this is a bit out of the topic of this talk, but we understand yet how debris flows volumes and sedimentologic and the sedimentologic characteristics of these debris flows. And this has been reported in some of the papers of our research group in the last years. But what we do not know yet is where erosion happens. So I spot this pink area here, because we do not know if this spot is here or it might be another way. And we also do not know in an ephemeral drainage system which of the channels are active at the regional scale. So, and we do not know, as I was pointing it out, where and when it rains at the regional scales. And to know it at a sufficient detail, which allows us to track the sediment dispersal within these watersheds, let's say. So what I propose you, before showing some of the results, is to go into one of these watersheds. This is one of the big ones. This is the Copiapó River here in continuous line. So this is a perennial river, but we see in dashed lines that we have most of the catchment has ephemeral channels. And the picture that I was showing at the first slides would be a bridge which is in this town here, which is Copiapó. So importantly, we cannot, if somebody wants to do this, is welcome, but to understand where change happens in this watershed, which is almost 11,000 square kilometers, it will take years of walking the area. And I say this because this is quite remote, although there is some big city here. We still do not have any detailed topographies of this landscape, so there's no way of doing a regional understanding or having a regional understanding of where surface change happens. So I can show you some examples. So for example, here we see some slopes, and every dot is the picture which is indicated on the left. And we see that these dots are very close. I tell you that they are less than 1 kilometer one from the other, and the regolith characteristics are exactly the same. The morphometrics, let's say the morphology of the slopes is, as you can see, quite similar. And we see that in one of them, there's a pervasive presence of rilling, whereas in the other, there are some small rills, but it is not showing in a such short distance. It's making us things complicated, no? So, given that we know that the conditions for rill formation are the same, we need to think again that this is something which is related to the intensity of the rains and we do not have information for that. So we need to still looking onto that. And similar, it happens when we look at ephemeral channels. So we see ephemeral channels that they experienced, for example, for the March 2015 event, a strong change, and others that didn't. And we see it because we can rely on we can see that this is stable because we have a lot of let's say continuous aeolian features that indicate that this is not having any significant flood in the time span that we've been monitoring them. So what we want to have surface change of before and after an event. This is what we want, but I will tell you which are the tools that we need to use. So I'm talking about synthetic aperture radar, and I want to use, or I would like people to use this technique, this approach in drylands, because it has a high spatial and temporal resolution, and meaning that we can cover regional scales in a high temporal resolution, and it works no matter if it's light or dark conditions or the weather, or it's cloudy or it's not cloudy. So the weather conditions, we do not care. It is free to use because it's provided by the ESA. And again, future missions are thinking on continuing this kind of acquisitions of SAR image acquisitions, and using SAR avoids possible limitations of classical optical imagery analysis, because optical relies on the spectral reflectance of the natural surfaces, and these surfaces are influenced by the minerals. And once we take out the first centimeters of the cover soil, we're still on the same soil. So in let's say deeper layers, so it makes difficult to identify erosion processes. Although there are some attempts in that sense, I would say that there is something more promising, which I will be showing you in a bit. So first, I would like to think we do not need to get into much detail, but a SAR image pixel incorporate two things, which is the phase, which gives you information about the distance between the sensor, which in that case would be the satellite, and the surface, and the amplitude, which is related to the intensity of these waves when they are backscattered towards the in that case to the sensor. So when we compare pairs of radar images at different times, this is known as interferometric SAR, so that we know from its acronym, so we call it INSAR. And the thing which measures, the parameter which measures this phase stability between pairs of images is what we know coherence. And coherence is very subtle to changes in the surface, and it's a dimensional parameter which goes from 0 to 1. I will show you some examples in the next slide. And as a hypothesis, this needs to be very stable before the events, of course, in arid areas. So I will show you if that's the case. Yes, okay, that's the case. So here, from 0 to 1, we see an area, a study area, which was published in a paper in 2020, where we see towards the red, this means that these areas are stable areas, and blue areas are areas which are not stable, meaning that between these a pair of images, the surface is changing. And we can see that there are quite a lot of areas that change, but most of them are related to the perennial river that I was showing you in the previous slides. And these areas here on the west, so on the left of the image, will be related to aeolian activity from dune fields and other examples, which I will explain, or I will show in a bit also. So, okay, we know that. And what lacks is that because this coherence of the phase, measuring the phase stability is not something that I have invented. It's been invented long time ago. But before I move forward onto the talk, I would say that the first attempt to understand this or to treat this as a statistic under a statistical approach of the coherence time series, to produce coherence change detection maps for retrieving erosion after single or individual rain events. Our work is the first one that has done that. But this information here will also have, as I was telling you, a lot of information which is coming from the permanently disturbed surfaces. So, but if we treat that in beforehand, we can mask this information from the resulting map. And if we continue the time series to the, let's say, after the event to the future, we will also be able to work out another parameter which influences a lot the coherence between images, which would be related to the rain itself when it wets the soil, because it changes the dielectric of these soils. So we will need also to get rid of this contribution of the moisture. So first, I will show you how moisture leaves, it dries. So this would be the 24-day coherence map after the event of the March 2015, and we will see this. Excuse me, because of these white lines, they are drawn a bit in a fast way, but what they want to show you between only 24 days, I mean only 1 month and a bit more and a half, let's say, after the rain event, they shrink a lot in area, meaning that we can also mask out on the map that I want to show you in a bit, these areas that it's not permanently, they are not affected by erosion, but they are affected by the moisture itself on the soils. I hope it was clear just in that ways. But how it looks, how a pixel looks like, this is something also I think it will be very helpful to understand this technique, is that an area which has a permanent loss, so we can track this, for example, a pixel which looks, which looks like that. And before this event of 2015 March, we see that there are high values of coherence, close to 1, but after the rain event, they always remain low, meaning that this change remains permanent against the primary image that we use, which is from before this event. Whereas when we are in areas where the change is recovered, so we have a temporary loss because of moisture, as I was showing you, we have a drop, but then we have a recovery. This is a bit more complex because it has interaction of probably clays being formed or redistributed in the soil, but let's say in a simple way, it recovers to higher values. And we see areas where it drained, but there is a rocky surface, so water doesn't make anything, it dries immediately, so they remain stable. And these are the examples of areas that would remain, or that would be masked from the non-stable areas that we can see at the slide where we had these aeolian fields that I was talking about, or the anthropic or vegetation growth, which is mainly related in this area to agriculture. Okay, said that, this is the map that finally comes out. And what is interesting is that it takes out all these, or it masks out all of these areas that we are not interested because it's not related to erosion from this event. And so when subtracted to the mean, which has been calculated by the stability, the images from before the event, what we get is pixels that go into the much negative, let's say, from the mean, so giving an idea of areas of more intense rainfall were localized in this kind of erosion hotspots. I hope this is the right word. And they are really the variability in space of their distribution is quite high. So we do not have any regionally extension of erosion. Instead, if it's more related into spots. And if you see after or downstream these spots, we see loss of coherence in all the ephemeral channels that drain the sediments and the water downstream. Okay, so that would be the example for the 2022. We've done that also for other events, and that would be the oblique view, if you want, with masking the previous map. So we would be seeing this same picture, sorry, and we would be having these hotspots and these ephemeral valleys being active. So this is one side. This is one side of what we've been working out, trying to understand when and where this change happens. And now I want to bring you to what happens on these ephemeral channels in particular, by means of understanding grain changes before and after this the flash floods that pass through these ephemeral channels. So again, we understand the before and after now, with all the exceptions and the considerations that I've been referring. And now it comes to something which might seem a bit complex, but I will try to explain point by point. So if we want to understand what change means in terms of grain size on valley floors, we can rely on the hypothesis on that the SAR amplitude, which is the intensity of this backscattering that is reflected back to the sensor. It's a proxy of surface roughness, and surface roughness we can have a proxy of this by surface grain size distributions. And the idea is, if we are in a surface, let's say smooth or flat, with more fine sediments present on the top, we would have no return, so we would have a specular reflection. Whereas when we are in a more rough, with more coarse sediments on the surface, we would be into a stronger return to the sensor, reflected on higher values of in decibels of amplitude. And we can shift from one to the other, and this is the idea that I will expand in a bit. But I will also put you into So also in that case, moisture will be contributing. So we will need to look at it, but also we will consider, because reworking can happen after the rain itself, because it can still drain water for some time, or then the fine sediments available might be deflected by eolian processes. So we will be also incorporating the reworking process in the understanding of this. So if we put this into examples on the field, we would have one example of specular reflection would be on the left, whereas when we are going to more rough, so more coarse dominated these grain size distributions of the surface, we will be ranging in different end members, let's say. And these arrows, they are only indicating that we can shift during these events from one type of surface towards the other. And this is what we want to work out with SAR amplitude. So for working this out, we went into the field, sorry, and we did grain size sampling in that case into a surface example. So this would be the channel, and this I have named this floodplain, but it would be a flat surface, probably first bits of the flood and then incised, and that's why we have this, let's say, braided or barren soil topography, whereas here we have a flat with boulders on top surface. And this is what we did on the field. We extracted this grain size distributions, and this is from one example. The Serna is the name of the valley. And if we go and look out or try to see how it SAR amplitude during the stable periods, I will come back in a minute, reflects with, for example, with the 84, we will be able to extract a lot of information. So first, these are time series. This is time zero. So this is the event that we are talking about, 2015, towards the future, up to the late 2022. And this is normalized amplitude. But here, these black squares, they indicate only where grain size were measured in the field. And this would be the rain recorded events. So there is nothing more, not much happening during this time. But the idea here is that when we are, for example, in a valley with flat, with these flat, let's say, surfaces, smooth surfaces to the radar, we would be in these lower amplitude values, while we are in more rough or more coarse, let's say, dominated valley floors, we would be in less negative amplitude values. And this is a nice correlation, but the interest from this comes when we go into the whole time series without this very ugly mask that I put you on. So if we go before the event, we have, for example, areas, pixels that follow this trend. So we have this event, and we have a drop here, and this permanent amplitude change, we can interpret this as this geomorphic event, so this float changing the grain size. So here, this particular example shows the initial condition would be a valley floor with such grain surface distribution that changes into this final grain size conditions, and this means that SAR amplitude time series allows us to map the quantitative change in grain sizes. And if we convert this into a spatial information, then we will have, this would be the D84 map for before the 2015 March event, where we will see that it's mostly dominated, this segment, this valley floor segment is mostly dominated by coarse sediments on the surface, whereas after the passage of this 2015 March flash flood or flood, we have a finding on this valley floor segment. So this is also something I believe it's quite interesting. But then there's something else we're still working out, is about, because I was showing you first this example, but now when we look at this other valley floor example, we see that there's a transient change in this amplitude, which must be related to something which comes back after a while to the pre-event, must be related with something dynamic, and we relate this to the moisture of these soils, of these surface soils. And this means that, but we have, and this is interesting because different events have different responses, but as I said, this is work in progress here, but the idea is that we could also allow, by using SAR amplitude, we could also work on constraining, let's say, spatial and temporal hydrologic events, so rainfall and floods, that do not contribute or that do not produce major geomorphic changes. And in order to finish this talk, to be fair with the time, so the concluding remarks that I've noted here, that would be that SAR amplitude has a potential to study these hydrogeomorphic events in these arid zones. Coherence change detections helps us to map the patterns, let's say, of erosion. We have examples of March 2015 and March 2022 already available if you want to check them on the literature. And this allows us to better resolve the footprint of storms, better than the rainfall products that we have available in these areas. And also that permanent amplitude change tracks surface grain change in drylands. So we can interpret this, or we can aim to interpret this as erosion and deposition areas along the channels, and that transient amplitude changes may also allow us to understand the moisture dynamics of these different surface types. And as I told you, this is something which we still work on. And well, thanks a lot for your time.
Thank you very much, Albert, for a really, really interesting talk. So just for everyone's reference, if you do have any questions for Albert, if you'd like to post them in the chat, that would be great. While people perhaps think about what they want to ask you, Albert, I have a quick question, if that's okay. I sort of was looking a little bit at the photographs that you included of the various grain sizes that you're considering, and I just wonder if you could comment on, I guess, like how the sort of the mobility of boulders in these flood events, or are you sort of primarily looking more at sort of gravels and smaller? And do you have any sense for sort of the mobility of sort of larger clasts versus that sort of finer material? I realize that might not necessarily be exactly the focus of your talk, but yeah.
Yeah, I've been looking at the mobility of large boulders, but some of the boulders that you've seen on top of these surfaces were already, let's say, they were already there, and they just been the valley just been filled up during the event, and then just again incised on the channel that cut through the first bits of the event, of the sediments from this event. So they might be coming from the sides, from the valley sides. Okay, so this is one thing. So we need to look at the lithology of these big boulders to be sure that we are not confusing them with rolling boulders from the slopes. But of course, in some of these catchment of some of these valley floors that I've shown, in particular the one that I've shown the grain size distributions, this is the one where, because it happened or because it was preserved, we have the opportunity to see the first deposition or the first sources, sorry, of this flood. They were more related to cohesive flows, so probably having enough competence to transport big boulders, meaning that I'm talking about cohesive debris flows or something, let's say, properly cohesive, high density, low viscosity flows. Whereas the next or the following sources that during these storms happened, they were more diluted flows from hyperconcentrated branching to water flows. And that's why we would see these two modes of sediment transport. We've seen that very clear in smaller catchments, in particular on alluvial fens. But here, to be honest, it's difficult to preserve, or it's difficult to find valley floors where this is preserved. Let's say, if you do not rely on such approaches, because if not, it's like a lottery or walking or riding with your truck long distances along the.
Okay, thank you very much.
Yes.
So we do have a couple of questions in the chat. So if I just read the first one. So this is from Katie Burrows saying, great talk. In your amplitude time series, which she says thinks it might be slide 29, did you have to mask out periods where soil moisture changed, or are the amplitude changes from grain size change much larger than amplitude changes from soil moisture change / it just didn't rain?
Yes. Well, the time series consider or include both, let's say, processes on the analysis, but at the point where we did the sampling, which is the same time where we consider the final time, which is the time where we rely to get our grain size correlation against amplitude. This is a period of time which is completely dry, the system. So we do not need to care about moisture there. And the same for pre-event. So when we compare before and after, but after meaning it's almost 6-7 years after the event, we do not need to care about that. But probably when we are, if we are in between these 2015 and 2017 events, we will need to take more into consideration. So I'll go to the presentation. Yes. So we would probably need to do it for each let's say stable period and see how it works out. But as I told you, the time spans that we consider, they are, let's say, moisture free. And thanks, Katie. Nice to hear you. From you.
We also have a question from Ian Evans, who's first complimenting you about your from your mapping technique, and asks if it can be applied for erosion in farmed or forested areas. Would it be more difficult or is at all feasible?
Okay, I reword I will say the question so just be clear that I understood it correct. So this person wants to know if you can do this in forested, vegetated or more vegetated areas.
Exactly.
I'm afraid that it would consider or you would need to consider masking large areas which are permanently losing coherence, and vegetation usually falls in between this group. So you would be losing a lot of area where you would be interested in studying, and you would only end using bare soil or bare areas, which will be a bit patchy and might would be not giving you the whole framework of sediment removal during a particular storm that you are interested. So I would say that this would be very interesting only to remain to vegetation or scarce vegetation areas, such as the ones that I presented.
Thanks, Albert. I'll go on with the next question, and I hope my internet is stable enough and that you can understand me clearly. This would be carrying a message from Aaron Buffer, who thanks you for the talk. And he's wondering if you can also detect grain size changes, if you can get quantitative maps of grain size across large spatial scales without any change. That means just using the same technique, but without before after. And
okay,
whether this is a matter of calibration in the field.
I would say that that we are not, I don't think luck is the right word, but we know that change only happens in a particular moment in time, in the sense of how sediments are, how sediment change in these valley floors. So this would be the first thing, which helps us to understand that this is a particular moment in time with these changes. But it is true that I hope I can answer it answers your question, but it is true that in some areas we've seen that, because if you remember to this reworking thing, that process thing that I was talking about, we've seen that we can also track some sediment transport signal which lasts longer than this event, probably some weeks to even some months, or because of the snow melt, probably of the high mountain ranges, you still have some water flows. And while the grain size doesn't change, let's say, strongly, we see that there is a slight finding, because probably you are not being able to transport big or coarser sediments, and what you are doing, you are just doing some kind of reworking. So you are just filling up, for example, these barren soil topographies, probably with finer sediments. So this would be something more dynamic grain size, which might be answering partly your question, I hope.
Can you hear me?
Yes.
Can you hear me?
Yes.
Yeah. Okay. So then maybe just to clarify, maybe my question wasn't clear. So I guess I was asking whether you could mean, you've been looking at the change in amplitude and therefore a change in grain size, or inferred a change in grain size. And I was wondering if you can just like get the grain size from the amplitude directly without, you know, looking at a change. Basically, getting a calibration for a given amplitude means a given grain size on the surface of the Earth.
Yes.
Right. Okay.
Completely. This is why this thing works quite good, because we are only considering we only have grain size from before. Unfortunately, we weren't there before the event, so we have only the after, not the before. Sorry. So yes, you can do grain size mapping from this, and this is nothing new. It's a lot of literature working also in rivers with sandy patchiness by Benjamin Purinton in the Toro Basin in Argentina, but also for relative dating of abandonment of alluvial fan surfaces in the Dead Sea, for example, as long as I remember now. But yes, you can do that at any time. You only need to be aware that when you produce the time series, you don't sample in the periods that still encompass information which is related to moisture. I think this is more close to what Luca was expecting me to answer. Yes. So yeah, I would say you will need to produce longer time series because you want to avoid these periods. Yes. So
yeah, makes sense. Thanks.
It will work. Yes. Okay.
Cool.
Sorry.
Thanks.
Thanks for clarification.
Okay, and then we have another question in the chat here saying, what is the resolution of the grain size mapping? I.e. in your desert areas, what's the typical number of echo per kilometer squared?
So again, sometimes it's yeah. So if I understand correct, there's a person who wants to know the resolution of this kind of maps or the resolution of what we sample on the field. Sorry.
I believe they say the grain size mapping. That's it. Yes.
Okay.
What you're showing.
So
yeah.
that would match the resolution of the available sun amplitude images that we use, and these ones here are somewhere around 20 meters per pixel. So this information would be to the information of a pixel of 20 by 20 square meters. Yes. You can go into much detail. I believe you can check Benjamin Purinton's paper. He even goes to finer resolution because he uses other SAR bands, which might be giving you coarser resolution. Finer resolutions. Yes.
Now we have a question from the moderator, in fact. Is there a rapid growth of vegetation after a rain event? Like if you have one, also is it picked up by INSAR or not? And in which case is it a problem, or is it just an opportunity to measure short-lived response of the flora that is otherwise hard to survey?
Yes, that's an interesting question, because if I will try to move fast to some slide where I show that. Sorry, I think it's somewhere. Yeah, probably here. Sorry. So there's a concern, because this is something which is very nice. I haven't shown any picture, but there is the desert blooming, which is very typical from after this kind of rain events in Chile. But it only happens in really stable, let's say, flat or some bajadas that we can have on this area here. Whereas in ephemeral channels, it's not very possible, or it's not really possible, because the instability of the system itself make the seeds probably travel away, so you do not see that much on the channels. And the other question the other vegetation that might be growing, if you see, this would be a pre-event surface, so you already have some vegetation that was not affected by this flood, only by some mud flows that just overspilled to the old or to the pre-surface. But then after the event, you only have some minor shrubs that they are probably mostly developing on the areas where sometimes some runoff happens because of minor rain events or snow melt on the higher ends of the catchments. But this would not be this would not really be a problem here, and this would not even be a problem if you move towards the north. So of where some of the examples that I have been showing you also. I mean, you have a complete lack of vegetation, at least on the channels. Yes.
Yes, thank you. I also had oh, Luca, you wanted to say something? Yeah, thanks. I also wanted to ask a personal question. I was just curious when you saw like there was rocky outcrop, there was also like 2 other categories, and I was and you saw that in the rocky outcrop there was not so much decrease in, I don't remember if it was amplitude or coherence. I was just wondering because there's still some kind of decrease, and I was wondering what could be the reason for that.
Sorry, it's correct. I mean, the slide that I'm showing you is the one that you are talking about.
Yeah.
Okay. So your concern is on this. On the rocky one.
Yeah. I was wondering what is this decrease if it's like supposed to not decrease.
Yeah, but this decrease it is probably because, I mean, when we look at this time series is a bit more than 1 year, whereas the others they are up to 8 years. So probably the variability of this signal, of the coherence signal, and here in particular, because if it's in a steep terrain, that would be even the coherence would be even more sensitive to the temporal coherence would be even more sensitive. But the idea is that we are not showing a lot of variability here, which might be this, which might be this, because in absolute values it's less than it's less than 0.1 units. So it's not significant from what we are seeing in areas where there is a permanent change. Yes.
Okay, thank you.
Okay, thank you very much, everyone. There doesn't seem to be any additional questions, so perhaps we can bring this session to a close. Thank you very much, Albert. I really appreciate your time today, particularly as well that you've talked about ongoing and current research. I think it's always more challenging when you're presenting something to a group like this when it's stuff that you're currently working on rather than something that you know has been published. So thank you very much for talking to us about what you're actually working on right now. Really appreciate it. Okay, and so thank you very much. With that, I'll just end the seminar here and hope to see you all next week for a slightly different style of talk as we jump into tectonics. Okay, thank you very much, everyone.
Thank you.
All right. Bye-bye.